Hello everyone, welcome to Engineers Ireland. We're going to continue obviously chatting about algebra, but today it'll be a bit different because we will show you that algebra naturally walks and leads you straight into complex numbers, and we will also be basically looking at more of how to solve problems in algebra. That doesn't mean we'll be looking at the Leaving Cert problems at the moment. We won't. We'll do that later in a few months' time. But what all of this comes down to is studying anything is a bit like cutting a piece of wood with a saw. Now, I know it sounds like an old country sort of thing, but if you think about it, if you have a hand saw and you want to cut a piece of wood, it would be very foolish of you to think that in one swing of your saw that the piece of wood will just fall away. It doesn't happen like that. What happens is when you move the saw, if the teeth of the saw engage with the wood, it'll cut that little bit, a small piece. Every time you move the saw, the teeth should engage. The parallel is as you study. When you look at something, a chapter or whatever it may be, it might only be a paragraph in something, your task isn't to completely absorb and understand everything in one move through it. You should take a pass at it, get the broad ideas. The next pass should go a bit lower, the next pass should go a bit lower. In other words, each time the teeth of the saw should bite. And the teeth of the saw, in our case, is your attention. There's no use going back over something, going, I'll be grand and I'll be finished in time for something. That's no use to it. You have to sink the teeth into the piece of wood. So, on that basis, we can, for argument's sake, just start with one of the things that I think is central, and we've looked at them before, our indices, but I just want to show you one example before we move on. And again, it's in Aidan Rowntrie's maths book. And you will find, when you look at it, it's one of these things that I like to harp on about. Okay, what we want to do is we want to find how our main terms here, this one for example, this one, and similarly the two underneath the line, how do they relate to each other? Now I know we've discussed this a fair bit, but I'm coming back to it again because there are so many chapters where you need to have a clear understanding in this. So the idea is we're looking for relationships here. Now, it's actually very simple. What you want to find out is, or understand, is what's the basics of things. We know, if you remember from before, let's say that x cubed, we could call it, oh well, it's 3 of these guys. And that's the same as saying it's 1 multiplying into 2 of them, or you can vary it any way you like. What does the bottom line look like? 2 to the n. Well, that will be 2 by, and we can go bracket 2 by, and lots, and we can imagine that there's lots of n's. Now in reality, n might only be 2 itself, but it's any number of them. So we're saying 2 to the n is a whole load of these 2's until there's n of them. I can pull out one in the front, no problem at all, and the amount I'm left with is 1 less than that number. So it's 2 to the n minus 1. So I know our 2 to the n is equal to, so we know how to deal with the lower line now. Now the interesting thing is, if I go straight back to my line of mathematics that we're working through, and I plug it in, I will have to go and rewrite all the top bit so that it allows me to put it in. Instead of doing that, what we'll say is, okay, I know what this is. I can take away a 2 to the n from it. And all I have to do now is name this thing. 2 to the n can have any name at all. You can call it an apple. So we're saying 2 apples minus an apple is an apple. I know that the answer that I have will be 2 to the n minus 1 underneath the line. If now we put our attention to the upper line, and we're saying there's 2 items I have. I have this guy, and I've also got, and we want to find out how do they relate. Well, we do know that 2 to the n is a whole succession of 2's multiplying into each other until you have n of them. And I want to be able to find a relationship with this guy. So, if I bracket it that way, if I had n of them together, that means there's n minus 1 of them in here. So I know that 2 to the n is 4 by 2 to the n minus 2. I can rewrite the top line. Call that an apple. Call that an apple. 4 by 3 is 12 apples minus 4 apples is 8 apples. Now, there are other ways of doing this. And if I looked at that equation, I could write out the answer straight from it. But I'm just wanting to break things down and show you that in a short way, using a simple system, you will get to the right answer without fail. And to begin with, that's what you want to practice. Shortcuts always come in after you have mastered the straightforward technique. So all we're saying here is 3 by 4 minus 4, okay? And I've deliberately been looking just to find common numbers, okay? I'll show you a slightly faster way now in a second. So we're saying that's 8 by 2 to the n minus 2. That's a situation where I have looked for a common thing, which is one of the items that we have here. It was either going to be this one or this one. Let's look at it a slightly different way. And I'm showing you this so you can see that there isn't just one way. And if your mind finds a thinking system through these things, that's the best one for you. If instead we now examine this last term here, and we're saying it's 4 multiplied by 2 to the n minus 2. Let's reverse our reasoning, and we'd say 4, that's 2 to the 2. The other is 2 to the n minus 2. So that's 2 to the n, which happens to be this guy up here. So I'm saying 3 apples minus an apple is 2 apples. Our equation now becomes 2 to the n divided by 2 to the n minus 1. You can do it in many different ways. You can bring out a 2 up top and say it's 2 to the n minus 1 all over 2 to the n minus 1, and these cancel and you're left with 2. It's very important that you play with these things. When you play with them, you can actually find that there's no real deep thinking in these, but they are a central part of how you dig into and get answers out of many different sections in the book. One of the things that you have to be careful of in algebra is when you're dealing with surds. Now, most surds are pretty straightforward. The only ones that you kind of have to look at and have an interest in basically fall into ordinary sort of fraction problems. When you have a surd underneath the line, and we basically discussed this before, let's just pick for argument's sake just say 5 plus root 2 all over 2 minus root 3. And you want to get rid of the third part underneath the line. Remember, we mentioned you can multiply it by 1, and 1 is in the form of something divided by something. And I'm just coming back on the difference of squares because this is a really important issue. Difference of squares is a minus b, and we know that's a minus b by a plus b. What are the issues? The issues, and why this is such a powerful tool, is we have a power of 1 here, a power of 1 here, a power of 1 here, and a power of 1 here. And they all convert across to a doubling of the powers. Okay? So we think of it that way. Let's just say to ourselves, what if I had a cubed minus b cubed by a cubed plus b cubed? Let's say, okay, I'll double my powers. That's all you're doing. Let's come back to our problem. Underneath the line here, we have a third, the square root of 3. How do you get rid of it? You look at this as being one of the two factors, either a one of this or a one of this, for the difference of two squares. So I'm looking for this guy's conjugate. So what we will have is 5 plus root 2 over 2 minus root 3. And I'm multiplying by 1 in the form of the conjugate of the lower number. It's easy to immediately say to yourself, okay, I can multiply these out down underneath here. You don't need to, because you already know the answer to this. It's going to be 2 squared minus the root 3 squared. And we all know that's 4 minus 3. So we just have 1 underneath the 9. That makes life nice and handy, and all we are left with now is a multiplication problem on the top. I'm back onto this because trigonometry and several other sections makes use of the difference of two squares. Why sections use it is we can go from one level of powers or indices to a doubling of them. Everything on this side of the equation has a doubling of powers. Any other combination other than these will leave you with something like, we'll say, a 3a, or a 3ab, or something like that. This is powerful because it does a complete step up in powers. When we were talking about about indices, and we were, let's say, looking at x to the n, the one thing that we didn't really say is, okay, this is the base. But what is it? What number is it? It can be anything, any positive real number. So, it could be e. And e is a bit like pi and root 2 and all of those. It's a number that goes on and on and on. But e is also like pi because it's one of the most powerful numbers that we have. And once you're in college, you will actually find that this thing crops up all over the place. It's about 2.717282828. You don't have to remember all of that stuff. It's irrelevant. Your calculators have e in it. So if we're saying x to the n, that could be e to the n. You have to go all the way into calculus, into the chapters on calculus, before the exponential function is discussed. To me, it's better to discuss it while you're dealing with algebra, because it's just a particular case of your ordinary indices, where we're just saying, instead of just an x, which can be any real number, positive real number, we're basically saying now it's going to be this very special number, e to the n. In relation to the logs, when you have a to the b equal to c, how that relates across to logs is we're saying this is a base, that's an index, which is also called a log. So we're saying, these indices allow me walk in one direction. If I know a base and I bring it to a certain power, like x cubed is 1000, I can find the 1000th answer. There are other types of problems where you know this side and you know the base and you're trying to hunt for your index. That's where logs come in. Log to the base a of this number c. All that is saying, and the best way to interpret logs, is the log is asking you, when I have the base a, what power do I need to bring it to give me this thing as an answer? And we know the answer is b here, because that's what we have it set up to. I'm back mentioning these again, because no one has told us what this base is. And it can be any one of a whole load of things. It can be base 10, base 2, base 17. It could even be base e. So, for example, we could have log to the base 10 of whatever it is. We would just say 10,004. That means 10 brought to this power of 4 will give you 10,000. We could also have, by way of an example, said log to the base e of something, we just call it the c, is equal to some answer. This is also it's only discussed out in calculus, and to me it really should belong to algebra, because it's no different to talking about these guys down here, only we're now naming the base. We're saying it's base e. Now, because it occurs so often and it is so important in engineering and science, and because engineers and scientists don't believe in wasting their time, they're always going for shortcuts and things, log to the base e of anything is normally written a bit different to anything else. That's the same as talking about L e. So the natural log is log to the base e. So there's two sections out in calculus which you can now immediately go to. You can read, and what you will find is, there's 5 laws about the, let's say, indices to the base of e. In other words, talking about the exponential function. They're exactly the same as the laws relating to indices in algebra. Go on a few little pages and you will find the natural log, this guy, which is just to the base e. It's only a number. That's exactly the same as our discussions in algebra dealing with a base a. You'd find, 5 laws. Well, they're the exact same 5 laws. So you don't have a brand new set of things. All you've done is you've named the base. What I want us to do, because I wish to, just for the moment, to lead us on into the first half of complex numbers, I would just want to get back to moving graphs around the place, because, after all, it's going to give you some visuals. If we look at the basic parabola, the basic second order, that's going to be the y-axis. That's the x-axis. This basic parabola is y equal to x squared. And there's nothing added to it. It's not like x squared plus 3. And as we'd know, when x is nothing, y is nothing. When x is 1, y is 1 squared. So it'll be 1, 1. When x is 2, y becomes 4 and starts to get bigger. Now then, that shaped graph here. If I could catch that graph and pull it down the way, what will happen? So you get something like this to it. You always need a little bit of imagination to interpret my diagrams. But the good news is they're fast, and if you make little diagrams like this and your mind knows what you're doing, what you've done is you've put the visualization out onto a piece of paper. One of the most things that wears you down and you cannot afford in exams, is maintaining visualizations in the mind. It's going to really tire you. So you avoid it, you draw drawings. So all we've done here is we've caught this graph and we've pulled it down. And we've pulled it down by a certain amount here. We'll just say for the moment 4. So it's now sitting at -4. This one, this curvy line, that one is y equals x squared minus 4. Obviously, because when x is 0, y is -4. Well, what does this look like? The difference of two squares. So it's x minus 2 by x plus 2. That tells us that it crossed the x-axis at -2, and it's crossing it at +2. So, move it up, move it down, any way you like, and you can very readily find the roots of it. The other interesting thing you'll notice is that one root is exactly the same distance away from 0 as the other one is. There's a common step that you have to go. And this, the x-axis for us here, that's the spine of this particular graph. What you will find, sorry, the y-axis, what you will find is that for any point on the y-axis, you'll be going an equal distance in both directions, and if you do, you'll find your graph. So the interesting thing then about this is it's telling us, for straightforward parabolas like this, quadratics, that the roots are evenly distributed about a particular point. It would be, for example, the lowest point in this case, and for parabolas that turn this way, one of my great graphs again. I'll restart it, I think. For a graph that turns this way, and that graph will be a y equal to an ax squared and some bits, but that a is negative. When it's negative, it turns that way. The same reasoning applies to this, that when you find this point here, a certain point, you'll have an equal distance either side of a line through here, and you say, this is my basic parabola. And I can find it. Now, that's any way we move this graph down the way or up the way, things are balanced around the axis. We're only looking at down the way because we're wanting to get real roots here. What you notice is this one here has two real roots, that one and that one. If we now look at pushing that one back, there's only one point this first graph touched the x-axis, just one point right there. What that means is the two roots are the exact same, because roots are always where a graph touches the x-axis. The roots are the same. And you say, what are they? Oh, can I factorize this? Yes, I can. It's x by x. That implies x equal to 0 as both roots. Now, life gets a little more interesting when we look at what would happen if instead we had pushed our graph up the way. Now this graph never touches the x-axis. What do we know about it? Well, the roots of this are not real. We're looking at a situation where to solve these, you have to understand complex numbers. A general form of a quadratic is y equal to ax squared plus bx plus c. That's the general form, and for any given x you'll get a certain y. So we're just saying this is the function. It's called y, because we like to name things. That's the reason it's called y. Because it's much easier to say y than saying ax squared plus bx plus c. So we're just kind of being lazy, and we'll just give it an easy name called y. Now, we do know that for that general form of the quadratic, that we can always find its roots using this. all over 2a. Now we can split that into two parts. What we're saying is any root, the two roots, they have a common bit, and they have a certain amount that will either get added or subtracted. And that brings us back to the graph that we had earlier, which is this one, and say, here's a root, there's another root. One is a certain distance away from a certain point, and the other one. For any one, even if our y-axis is over here, and we're now saying, there's my graph, I know this x value here. That's the common bit. It's minus b over 2a, this x middle bit. And we're saying, oh, one of the roots is up the way bit, and the other one is down the way bit. That bit is this much. Now, we can happily, while we're doing algebra, we can happily deal with all of these that touch the x-axis, and even when they only touch at one point, but we're in real trouble when you get a one that's up here. That requires something different. What happens? Well, the kind of thing that happens is we'll finish up with something. For example, you can finish up that it's equal to minus outside of 1. This is just an example of it by the square root of 1 squared minus 4 by 1 by 2 all over 2 by 1. So when we simplify that, you're saying, oh, it's minus 1 plus or minus the square root of minus 7 all over 2. So we have a problem. And the problem is that the number underneath the square root is clearly there's an absolute infinite number of possibilities of square roots of negative numbers. You can have minus a million, get the square root of it. Now that's not a very nice position to be left in. So what do you do when you're dealing with these guys? And this is why complex numbers are, it's one of the little tricks in it that makes it actually so useful, is instead of having an infinite number of things that look like that, okay, isn't it much better to have just one problem rather than an infinite number of problems? So what you do is you say, well, isn't that the square root of 7 by minus 1? True. That is the square root of 7 multiplied by the square root of minus 1. So this bit is safe now. That's the square root of a positive number, and we can all deal with that. So no matter what type of square root of a negative number you're dealing with, all you do is you get the square root of that number and you're left with one problem. So what's the square root of minus 1? There's never been a person, and there never will be a person, that will have an answer to that. We don't know, but we can give it a name, and we can always do it back in maths. Now, if you think about it, it's a very odd thing that we should call some numbers real and other numbers unreal. Quite literally, these things have a very bad press. And the great German mathematician Cantor in the late 1800s did a lot of work on irrational numbers, and he did work on this kind of stuff, and quite a number of others. And they actually had a lot of ridicule in their life for dealing with these, but thanks to them, they have been given a good footing in mathematics, and they've been pretty well fleshed out and people know about them. The real issue, though, is if you're dealing with, let's say, designing an electronic circuit or sending men to the moon or anything like that, you can't do it without taking this little guy on board. But because of the history, we call these things imaginary numbers, okay? It's like when you're a kid with your little imaginary friend. It's a strange thing to think back that if you knew somebody with an imaginary friend, you did know at the time that adults would have, laughed at it and thought it was a silly thing. those same adults most likely looked up to scientists and engineers and mathematicians, and they've got imaginary numbers. Pretty sad, that one. So we can call this I. And I is just the first letter of imaginary. That's in keeping with the normal tradition, in the same way as when we say f of x, which is y, f is just the first letter of function. It's nothing more than that. We do this all over the place. We like to go for shorthand because it's easier to do your mathematics. So this guy gets called I. Now we go back to the roots of quadratic. You're saying, oh, x is going to be equal to, there was some real bit which we just call a now, and you would either have a plus one or a minus other bit. In this case, we'd say root 7 is going to be the b bit, multiplied by I. No one knows what I is. But we have managed to at least call this one and know it's a real number, not an imaginary silly thing, okay? And this is also a real number. We just have one embarrassing little thing called this I. But complex numbers are amazingly powerful. It's just unfortunate that we don't know what the square root of minus 1 is. So let's look at these guys and see, and we'll go through the first half of the chapter on complex numbers now. We won't do the second half at the moment because you really need to have looked at trigonometry first. But the first half you will find is literally, it's a paralleling of stuff that you've already done in your algebra. What kind of stuff would you have? Well, let's look at adding two of these numbers. Example. 2 plus 3. If I wanted to add that to, let's say, 3 plus 7, right? What do? Well, life's easy here. We can add the real bits together. They won't get corrupted by the imaginary bit if you add them together. They're likes, they're reals. We can add them together. Those two are going to give you a 5. And you get to add the imaginary bits together. Because, remember, that I letter, you can give it any name you like, you can call it an apple. Well, 3 apples and 7 apples is 10 apples. So, 10i. Adding them is easy. Add the real bits together and add the imaginary bits together. If we were, instead of adding, if we were taking away, it's the exact same process. The only difference is you can be taking a real bit away from a real bit and an imaginary bit away from an imaginary bit. So far, so good. Easy stuff, okay? Now, let's have a look at multiplying. Now, we'll do it in a slightly different version to the way you'd normally do these things. And I'm just deliberately picking small numbers to make my life easy, okay? Let's multiply these together. Well, first by first, 3 by 2 will give me a 6. Now I'm writing it in this line here, and this is going to be 4 real numbers down in here. And so what else do I get from this? 3 multiplying into this. I'm going to get plus 3 by 3 will give me 9i. So that's finished with that letter. Now, I want to multiply plus 2i into these guys. Plus 2i multiplied by 2 will give me plus 4i. I'll put over here the last bit until we discuss it now in a second. What do we now get if I multiply that guy with this guy? What you're going to get is 2i multiplying into 3i. 2 by 3 is easy. So we have 6i squared. So what is I squared? We know that I is the square root of minus 1. That implies I squared is minus 1. So that makes life easy. What do we also know? I cubed. What is that? That is I by I squared, isn't it? And this, by the way, is the same break things up as we were doing in indices a minute ago. So we're saying it's this by I squared, and I know what I squared is. So that's I by minus 1. So it's minus I. Oops, I'll bring it on the next line. And I will redraw this. What about I to the 4? Well, that is I squared by I squared. So it's minus 1 multiplied by minus 1. So it's 1. We can list these. And there's no other types. I to the 5 is just I multiplied by I to the 4, so it'll be I by 1, which is I. I to the 6 is I squared by I to the 4, so it's just I squared by 1, which is I squared, and I squared is minus 1. They're the only 4, the only ones you need to know. So, when we were looking at our numbers, and we had got the plus 2 by plus 3 will give me plus 6. Plus 6I squared. I know that now is going to be plus 6 by minus 1. So that's minus 6. And generally, you bring it over this side. Wheel it around here, I get minus 6. So now, all this stuff has been moved over here so I can get rid of it. And you add reals with reals and imaginary with imaginary. So I'm going to get 0 real plus 13. Multiplication then is not hard. All you have to know about multiplication is that I squared is minus 1. One interesting little thing about this is let's look at the the factors of the difference of squares. And we'll do it for complex numbers. Because there's an interesting little thing about this, and once you know it, then it'll make life easy, and we'll be able to step on into the division or the rational expressions in a minute. We do first by first, the same as you would have done before, first by second, second by first, and second by second, as before. A by A is A squared. A by minus BI is minus A BI. That's the first two. The next ones then are plus BI by A, so I get plus A BI. They, as you notice, cancel. And then I'm now left with my last bit, which is minus B squared I squared. What do we know about I squared? I squared minus 1. So what I have here is minus B by minus 1. So it's plus B squared. So the fundamental difference then is these two guys, these two binomials, binomial just means two numbers, these two binomials that are conjugates of each other, because in one of them the two numbers are added, like that one, and in the other one they're subtracted. A difference between algebra and complex numbers. In complex numbers, A plus BI by A minus BI is going to give you A squared plus B squared. Whereas in algebra, you've got A squared minus B squared. The reason for the change of sign is this little I character. When you square it, you change your sign. Why do we need to know this? Well, this is the secret for doing division in these guys. So we look at division. How do you divide a complex number by a complex number? Well, we go back to the very useful little factors that we have been dealing with in algebra, which were the factors for the difference of squares. Only secretly we know in complex numbers that these guys are actually going to be the factors of the sum of squares now. So what we want is to get this guy's conjugate. And we're going to multiply the expression by 1 in the form of the conjugate divided by itself. All of that here divided by all of this down here is just 1. So we're not changing our equation, we're just multiplying by 1. But the good news is, on the top of the line now, all we're going to do is multiply this by that, and we know how to do that. But in the bottom of the line, I have got two factors that are conjugates. Remember, so you don't even have to multiply these things out. We know the answers to them. It's going to be 2 squared plus 3 squared. Okay? Underneath the line. So life gets easy for us. And all it means is when we've multiplied out all the top here, it's going to get divided by 13. A very interesting thing about complex numbers, if you noticed what we got, how we got to complex numbers was a problem in square roots. Now, square roots, you would think, are the last thing that you want to start looking at when you're inside in complex numbers. They're not. The interesting thing is, there's actually square roots of complex numbers. We want to find out, for argument's sake, the square root of, let's say, 3 plus 4. How do you do it? How do you make sense of that? When you don't know something, you give names to it. We're suspecting that the answer will be a complex number. Call it A plus B. Right? Now that I've given a name to it, now I can play with it. I want to get rid of this square root thing here. So I'll square both sides. And I'll say 3 plus 4i is going to be equal to A plus bi squared. Okay? And what will that give us? A by A is A squared. A by bi is A b, right? Bi by A means there'll be 2 of these, and I've got b squared, I squared. So what I have is A squared minus b squared. That's making that minus 1. That's the real bit, plus 2ab. Like must be the same as like. This real number must be equal to that. This real number multiplying into the imaginary I must be equal to 2ab. So now you've got 2 simultaneous equations and you can solve. There isn't a big problem with it. The last little thing I just want to mention to you in relation to this is that, first off, instead of talking about x squareds and quadratic equations like that, we'll normally use z's. But if we, just for argument's sake, z squared plus z minus 7. Let's look at that. The number here, that's a real number, it's 1. That's a 1. That's also a real number. All 3 numbers are real. In complex numbers, or complex quadratic equations, when you've got all real numbers, you know that the roots of this are going to be a conjugate pair. In a different equation, let's just say 2iz minus 7. In that equation, or if I had 3iz squared plus z minus 7, or this kind of one, what you'll notice is that coefficient or that any of the coefficients, if you've got an I in it, it means that the solution to this, the roots of it, will not be a conjugate pair. There's a very simple proof to this. Now, rather than my going through a proof that is perfectly stepped out in the book, it's better for you to do it. What you should have noticed, though, by this point in time, is that complex numbers are just a natural extension of algebra. Just in algebra, as it's presented, you shy away from roots of a quadratic or cubic that will give you the square root of a minus number. Once you realize that you've got that, and all of those minus numbers, square roots of minus numbers, can be represented as a real number multiplied by the square root of minus 1, you're now in complex number land. But the rules are identically the same as they are in algebra. The second half of complex numbers deals with polar coordinates, and you really have to have done your trigonometry first. So we'll leave the second half of it, and we'll come back to it once we've dealt with trigonometry. You will be, at that point, you'll be looking at something called the Moivre's theorem, and it is an extremely powerful theorem. It helps the solution of a lot of problems. So that's something to look forward to, if, of course, you think in terms of looking forward to mathematics. And I would hope in a few weeks' time that you will be looking forward to it. Okay, see you guys. Bye now.